Hi everybody. Well, today we're going to show you some things about pendulums. There's conservation of energy. There's not that much friction, so we don't lose that much energy. And then there's the time that it takes to swing back and forth from one side to the next. The time that it takes to swing back and forth is determined only by two things. The strength of gravity, which here on Earth stays pretty much the same, and the length of the pendulum itself. A pendulum that is long is going to take more time to swing back and forth than a pendulum that is short. And all of these pendulums here are set up slightly different lengths. You see that right here. And so we're going to see some patterns appear and then reappear and then repeat themselves. So the front, having the longest, is swinging back and forth in the longest period of time, and the back, the shortest, swings back and forth or oscillates in the shortest period of time. And here you can see that the pattern keeps changing. But it's actually going to go back to what it was. I mean, the original. I think that's pretty amazing. The first accurate time-keeping instruments on Earth, well, some of them use drips of water, but others use pendulums. Grandfather clocks use pendulums like this. And we're seeing the conservation of energy. Here we've got other pendulums that we'll show you up close a little bit in just a minute. And here, their movement is actually recorded in the sand. This very fine sand underneath here is going to show us the overall motion of these pendulums. So here at the bottom of this pit and pendulum, you can see the patterns that were actually created. The way this thing's suspended, it will oscillate in patterns, that is, swing back and forth in these patterns. And I think it's just beautiful. Beautiful demonstration of this periodic motion. I'm going to start this thing again, but you can see the pattern we created the first time with kind of a swinging motion back and forth. That's how it starts. And it keeps doing that, repeating, getting smaller, smaller, more and more detailed over and over again. Still oscillating. It's a very fine-grained sand down there. Hi everybody, today we're going to have some fun with the pendulum. Here it is in its resting point. This is the lowest point it can reach. As long as these two ropes or either one of these ropes stays intact. We're going to add some energy and we're going to let go of it. But the energy we put into it is all the energy that's going to be in the system. So it can't go any higher than what we started off with. You ready? This is going to be you. I'm going to bring this right up next to your nose and I'm going to let go of it. Just don't lean forward. Because if you lean forward, it'll hit you. If you don't lean forward, it should just come up really close, almost hit you. We'll film this from a distance, then we'll do it again up close. Ready? And 3, 2, 1. And good job, nerves of steel. Awesome. So this is the maximum gravitational potential. This is all the energy that there was. If we let go of it right here, that'd be a mistake. Do that. Go that high on the other side. You guys want to see that up close? Come on over. There it is. Oh, enough to move your hair. The energy it took to move your hair, the energy in the things that you can't hear, like there's a little bit of noise from the rope, moving the air, heating up the rope, that all takes energy, and that energy is coming from the gravitational potential energy that we put into the pendulum. Now what's interesting about pendulums, one of the interesting things is the rate at which it swings back and forth is always going to stay the same. That is, the time that it takes to swing from one side to the other will stay the same as long as gravity stays the same and the length of the pendulum stays the same. If we shorten this, it swings back and forth faster. But pendulums are one of the first things used to keep accurate time, ever. You've seen a grandfather clock? Well, it's got a large pendulum in it. And the way that we adjust the grandfather clock is by lengthening or shortening that pendulum. The first accurate clocks in the world use systems like this. Some of the first accurate clocks. This is its resting point, right here. This is where it's going to try and go back to. And right now it's pointing straight down to the center of the Earth, because we've got just as much Earth in front of us as behind us, to the left, to the right, north, south, east, west. The only direction where we've got more Earth is directly down. And this would fall to the core of the Earth if it could. Now, we can try this. It's going to be the same period of time to swing back and forth. We could probably even see it in the video. But if somebody will stand on the ladder, we'll try this at a higher point, and you probably want to move out of the ladder. Ready, Jacob? I'm going to go first step. Let's see where this is. Let's see where this takes it. Right, oh, it's perfect. Right on your teeth. Ready? Got a good dental plan? Okay. All right. Yeah, I got going forward.
Pretty sure I got it.
3, 2, 1. And there it is. Oh, I didn't even really get that close. It's giving up a lot of its energy in that noise that I hear, right? The energy being released from that. However, if I was over here and I pushed on it while I was swinging, it would definitely, there'd be enough energy to cause some damage. Now, we'll show you an example of inertia here real quick. Take this out. Set this up right here, like so. And in there's some volleyballs, isn't there? Yeah. Is there a loose one? Or are they all wrapped? Volleyball. Oh, there's a loosey. Oh, yeah, there's one right here too that Jake has on. Okay, so I'm gonna swing this with as much energy as I can. I'm gonna give it quite a bit. When it hits this, we should see the trash can go flying, and it's gonna go off over there. What kind of energy does the trash can have right now? Gravitational potential. Perfect. We're going to turn that into kinetic. Don't try and catch it down there. Just let it go. 3, 2, 1.